Tonight's talk is digital storage memory for the Earth and beyond. So please silence your cell phones. That's something I tend to forget. A background. So how many people is this your first meeting of the ACM or SFBay ACM? So ACM is an international organization that was founded in the Bay Area in 1947. It's the Professional Society for Computer Science. So Association of Computing Machinery. So for all the journals of computer science, publications, conferences, research, that all goes through ACM. Like IEEE is a very good organization for electrical engineers. We're the corresponding for ACM. So our local chapter, professional chapter, has been founded in 1957. So tonight is our birthday. You see a birthday cake back there. So we're 68 years old. No, I've not been volunteering that long. We have only a $20 annual membership. I think when I first got involved in about 2006, it was still $20. So something we could talk about is a little bit of adjustment for inflation that has happened over the last so many years. You can see our upcoming talks with SFBay ACM on Meetup. And we have, I haven't counted lately, maybe 230, 250 past talks of our more recent talks on our YouTube channel. And so we shoot for 2 monthly meetings. It may be general computing and a data science SIG special meeting or AI meeting. We also like to support networking, job hiring announcements. So we're a nonprofit, so helping the community. We've done other things like in March, there's judging for a science fair for a 6th grade to 12th grade, where we're reviewing 1,000 projects. We need 20+ volunteers to review those. And we give a first, second, third prize to the students and also to the teachers to support STEM education. So yeah, cash. If you like us, give us a 5-star review on Meetup. We did the election. We have some location sponsors to thank. So Valley Research Park, that's this location. So we coordinate with them. So thank you, Valley Research Park. Relating to that, I would ask that at the end of the talk, many times people like to ask the speaker questions. Give him a chance to close down his computer and get to the tiled section. I have to close down some walls here and here for meeting rooms tomorrow. And so I'll have to move some stuff. So if everybody's congregating, that's kind of hard to do. At least walk closer to the pizza. When in doubt, go for the pizza. Another sponsor is RXM. They've been sponsoring a lot of the fees that we've had to pay for the location sponsor. So they do a lot of cloud native and AI training and consulting. So say if you want a Kubernetes class and the instructor to travel for 20 people in Berlin, you know, that's the kind of thing that they can do. So they're very specialized on large scale DevOps type of things. Another sponsor is Front Egg. So they'll do managing your cybersecurity identity. So I'll be monitoring the chat in Zoom for the remote audience. So if questions come up, then I'll read those. And periodically, as time permits, I'll try and get the speaker's intention and ask him. Also, for the audience here, any questions you have, I ask the speaker to please repeat for the recording and for the Zoom audience, because the speaker on the laptop won't pick up if somebody in the back of the room is asking a question. Also, don't get into a 2-minute context with a 5-part question. The speaker won't remember it. So be kind to our speaker. If you want to ask more than one question, your hand can go up another time. That's no problem. We always have an outstanding call for volunteers. We can start with small, limited engagements. Could be different areas that you're interested in. You know, if you like things around web stuff or working with sponsors or locations, or I tend to like following data science and AI, so I invite data science speakers as one of the people that does that. So there's a variety of ways that kind of overlaps between a volunteer's interest and some of our needs. We have an honor system jar for food. We ask for $2 per pizza slice. We have some upcoming events. The green ones are AI or data science related. Let's see. Yeah, so we have Wednesdays, tonight's one. Next week, Monday, we have a co-pilot for social promotion by Dr. Boris Galitsky. Wednesday, August 20th, also at this location, Valley Research Park is VRP, designing for scale, reliability, and resiliency, real-world lessons. And then on Monday, August 25th, we have When Bias Goes Viral, Protecting Your Brand from Biases in Generative AI. And Alok has got a paper he's published, and it's coming out in, I think, late August or September. So he'll be giving a presentation on his recent paper. So to introduce tonight's speaker and the topic, so there's a large ongoing demand for more memory. New and traditional storage technologies are developing. They'll improve efficiency and reduce energy consumption. Keeping more data for longer time creates demand for curation and preservation. So this talk will be on the developments and how they'll create new economic opportunities. For a background on Tim Coughlin, over 40 years in the data storage industry. He's running Coughlin Associates. He consults, publishes books, and market technology reports, puts on digital storage and memory-oriented events. He's a regular contributor to Forbes.com and very active in IEEE, a fellow, past president of IEEE USA, past director of IEEE Region 6, active with SNIA and SMPTE. So you can also find out more on his website. So please help me with a warm round of applause for tonight's speaker, Tom.
Well, thank you all. So I'm actually been an ACM member for just 25 years. So so I've been a member of ACM for a while, but I've also been a member of IEEE, and I've done a few things. Last year I was the president of IEEE, which is over 500,000 members in over 100. It's almost 500,000 members in over 190 countries. So that was quite an experience, but that's a whole nother talk to get into that. But I'm glad to be able to come to you tonight, and thank you for inviting me.
Yeah.
Digital storage and memory is stuff I've been doing since I got out of school, and actually in school. So and so I want to look at a number of different things. So I'm going to talk a bit about storage in general, some of the big drivers, storage, computing, networking. That's the stuff that makes the world go round nowadays, source of a lot of economic growth and opportunities. We'll talk a bit about the different types of storage devices, sort of a zoo, if you will, storage and memory devices, from hard disk drives, magnetic tape, flash and SSDs. Optical storage is actually about 5 or 6 optical storage startups right now, of all things. DNA storage, someone was asking about that earlier as well. Also a bit about some changes in architectures around, particularly around storage. CXL is changing the way that people design things, and memory is a big driver of that. NVMe, of course, is the interface, and both NVMe and CXL run on the PCIe bus. Then things that are changing now because of the slowdown of Moore's law, people are looking at doing things in different ways than they have in the past. So packaging of chips is becoming a frontier for new creations and capabilities. So I'll talk a bit about that, and especially how that relates to the way in which you might use memory. And then finally, a summary. So data growth exploding. IDC has done these projections of the amount of data being generated. I think the last one I saw was like 394 zettabytes of data generated annually by 2028. So that's apparently 3 times more than that was generated in 2023. Most of this data comes from IoT devices, sensors, cameras, things like that. And they have the most value when it's processed real time. That plus AI is going to drive the use of memory, where you keep things temporarily, but not long term. And but in a few percent of this data, or something resulting from that data, is going to be stored long term. But even that storage amounts are increasing as well. So greater use of AI in devices at data centers, but also at the network edge and endpoints, increasing memory and storage requirements, and also increasing the value of storing raw data for the training. So in addition to the growth of data being processed, power consumption as well as latency and data rates are important considerations in future system designs. In fact, some of you have probably seen some of these numbers on the power requirements people are projecting for data centers, for example, which I just saw. See, I think it was like about 2 or 3% in the US now, going to 6%. No, maybe 6% in the US now, moving to 12% is what I saw. I was just at the Pure Accelerate conference. I came back from there today. So this leads us back to look at storage and memory technologies, which will enable handling basically a data tsunami, a large amount of data that's coming down on us. So at the NVIDIA GPU Technology Conference in March this year, Jensen Huang gave some insights, for instance, on future memory and storage needs for future generation GPUs. So this is his basically, I think it's second half of 2027, it says there, for this device. It shows 365 terabytes of fast memory with HBM4E estimated to be what they're going to be using at the time, and delivering 4.6 petabytes per second data rates to the GPUs. So that's pretty hefty. This is the kind of stuff that people are looking at. Now, storage and memory processing, and GPUs are expensive, but part of that, and part of in general, is that storage and memory are a big portion of cost of servers or of support for servers. And they've got to be efficiently utilized by the best total cost of ownership. So the figure to the left gives some idea for traditional servers, at least, what these are like. And these devices have different life cycles. So if you're looking at how you can use them most effectively and get the most out of them during their life, then there's an important, ideally replace them separately. And I know there's some OCP activities that have gotten into that, basically building racks that where you only replace what you need to replace in them. So, but also this has driven the use of ideas around disaggregation of traditional computing, creating pools of resources that can be combined together with software. And CXL with DRAM and possibly other non-emergent memories. And storage pool would be an example of these memory pools, the storage pools, for instance, using NVMe over fabrics. So in addition, data access and on-chip data movement are costly in terms of energy consumption. So in fact, even in a GPU, you've got all those stacks of DRAM chips and high bandwidth memory. And so all those DRAM chips have to be constantly refreshed. And so a lot of energy is spent in refreshing traditional volatile memories. But the other side of it is that there's a lot of energy consumed in moving data around. So if you process data closer to where it lives, there could be advantages there in terms of energy consumption. So the figure on the right gives some ideas on that. So let's get into space here. So we need data, and we're going to be processing data here, but also as we move and do more stuff in space, we have to think about how we're going to be serving those resources. And Vince Cerf and other folks have talked about, interplanetary internet, but it'll probably require a store and forward messaging system because of the latencies and connectivity issues with communicating in space. You have to wait until you're lined up and you can actually transmit from one place to another. And so storage is going to play an important role in that communication for that point. But also as people move in outer space for exploration, development, and settlement, our data center technologies, the stuff we use to do the things we do every day, must come with us, in part because of the latency of communicating with the Earth. So if you're going to be out there, you're going to be doing something out there, you need lower latencies, and that's why you're going to have processing, memory, and networking in space. So there's companies like Lone Star and other companies developing space-based data center capabilities in Earth orbit, on the moon, and beyond. And some of these have crashed, but eventually they won't. And actually, there's a picture here, and several missions to the moon have included data storage and data center infrastructure. Here's one that actually landed successfully. I think it's because it's got a low center of gravity. The other ones, I think, are kind of stuck up in the air a bit, so maybe I made it a little easier to tip over. This is the Blue Ghost. It's a lunar lander mission launched by Firefly Aerospace. It's part of NASA's commercial lunar delivery program. So this lander touched down successfully on the moon's near side on March 2nd, 2025, in an area called Mare Crisium. Among the payload was an Iridia synthetic DNA, carrying tokens and historical data as a monument to humanity's achievement. So there's some storage in space there too. In that case, sort of archive or digital preservation. But not only that, there's other stuff with regard to preservation, bringing up that topic. Some of you probably heard about there's some Mount Vesuvius erupted in 79 AD and buried Pompeii is a famous town for that, but also a place called Herculaneum. And apparently there's some wealthy guy who had something like 1,000 scrolls in his house, and they got when that volcanic ash came down on that, it basically turned these things into charcoal, but they're still intact, at least until they try to take them apart to read them. So there's a few of these left that are not been destroyed by trying to take apart and read them. And recently they were able to uh, uh, use CAT scans, X-ray tomography, basically, and AI to be able to virtually unroll these things and start to read them. So there was last year there was a report on that. Some of you may have heard about that. So that's an example of recovery of ancient data. In fact, I think the one they uncovered said something about where Socrates was supposed to be buried, something like that. But also the digital data we make, it's not like paper, right? We can just look at paper with our eyes and we can read it, but digital data requires, the encoding, requires the technology that you use for reading and writing it. You can get it. So in a sense, it's fragile. So what can we do in order to, another challenge I think we face is what we could do to make data, to be able to do true digital preservation and be able to keep data for the long term. So it's another challenge that I think we face in terms of our civilization. So we got the outer space, we have reaching into space and also reaching into time in terms of our needs for storage. So let's look at the things we've got to do this with today. So you can look at this as kind of a hierarchy in a sense. There's fast memories, which are volatile memories, DRAM and SRAM. They can provide data very quickly with nanosecond latencies and as fast as 10 to the 7th megabits per second. So you've got the PCIe bus in computers. It's somewhat slower than the memory channels. So NVMe SSDs that run on the PCIe bus can operate at a lower performance, say about 10 to the 5th to 10 to the 6th megabits per second. SATA and SAS interfaces originally developed for hard disk drives, but even if you have an SSD with NVMe over PCIe bus, they have slower performance. Hard disk drives normally use SAS or SATA interfaces, and they're even slower performing than SSDs because it's an electromechanical device with mechanical latencies and access times, and their performance is generally in the 10 to the second or 10 to the third megabits per second. So that's one way of viewing it. Here's another way. This is a colleague of mine, Jim Handy. We do a report on emerging memories, and this is non-volatile memories, and this is one of the charts used in that. But it's showing a log scale. It shows log scale along both the horizontal and vertical axis. And the horizontal axis shows the storage price in the log scale. And the bandwidth is along the vertical axis. That is the actual performance of the device. So you can see more expensive per bit and faster cache memories at the upper right. That's those non-volatile or those volatile memories like DRAM. NAND flash is a bit slower than that, but less expensive. Hard disk drives in the middle, and tape, for example, is the cheapest, but also the slowest of all these things. So there's kind of generally a relationship there that has held for a long time. So let's start looking at these individual technologies. First, look at hard disk drives, magnetic tape. They're both technologies that are using the magnetic properties of materials in order to be able to record and recover information. So there's sophisticated electromechanical devices. You spin the disks around, and I've got a rotary actuator arm that moves across the disk to read and write the tracks on the disk surface. They can access data from multiple surfaces. They generally have a lot of disks in them. In fact, some of the nearline drives have 10 to 11 disks in them. They're recording on both sides of those disks. So it's got a head on that actuator that reads and writes the information on the disk. It's positioned, and it uses disk rotation and a head positioning to access data anywhere on the surfaces of these devices. So it's a random access device in that sense. And in fact, that was part of the basis of the name of the RAMAC computer, where these were first introduced back in the late 50s. So that was the IBM RAMAC. Hard disk drives take a certain amount of time to get to data. That's called the access time, or mechanical device. That time is comprised of the time to position the head over the right location on the disk surface, and then to be able to read or write information to it. The electronic board in the back of the hard drive, you can see that on the right-hand side there, controls the motors, creates the data to be written on the disk, and when this data is passed to the hard disk drive using the interface between that drive and a computer, it reads back data from the signals detected from that head read element. The electronics board also provides encryption for data written on the hard disk drive, detect and react to environmental conditions that could damage the drive, and controls the interface between the hard disk drive and the computer it is connected to. They're increasingly being used. They used to be used in a lot of consumer computer application, personal computer applications. But increasingly, where hard disk drives are used today is in nearline storage for data centers or enterprise applications with high capacities and low cost per byte. So they're currently up to 36 terabytes of storage. The latest generation of drives are using a laser to be able to heat the media surface when you're writing. They call that a heat-assisted magnetic recording. Seagate's been shipping those, and by next year, Western Digital and Toshiba will be shipping those as well. And in addition, and projected to reach 40 terabyte hard drives and 60 terabyte in a few years' time, and looking at 100 terabyte hard drives by the next decade, perhaps, with this technology. Well, I've got some bigger ones for you. And in addition, there's a technology called dual actuator hard disk drives, which actually it splits the current actuator and has them working independently, which could give you double the access speed on those drives. So that's a possibility. And in order to deal with rebuild times on hard disk drives, if these things get really huge, you may want to do that. So now hard disk drives there's a roadmap. There's one developed by the hard disk drive manufacturers. That's this ASRC is the latest one I've seen. It shows projections for that technology into the mid-2030s, moving from 2 terabits per square inch, which is basically where we are now, to over 10 terabits per square inch will enable hard disk drives that can reach 100 terabytes or more. Enabling these advances requires adoption of energy-assisted magnetic recording like that hammer, which enables stable high-density recording with conventional write elements, but on media that if you didn't heat it up, you couldn't write on it. It reduces the coercivity, the ability to write on the media, if you will. There also has been work done on multi-layer magnetic recording technologies. Two-dimensional magnetic recording is being used today to maximize the number of concentric tracks of data on the disk surface. They're also looking potentially at using pattern media to actually create patterns on the media to control the bit size even more. So these are some of the things on hard disk drives. So magnetic tape, it's actually older than hard disk drives. It's been used for computer storage since its introduction in 1952. There have been many versions of magnetic tape, from open reels to modern cartridges. Magnetic tape largely allows sequential access of data. You have to unwind the tape to be able to read or write it, rather than random access like hard disk drives or SSDs, solid-state drives for that matter. It again uses a magnetic recording technology somewhat similar to that used in hard disk drives, but with multiple tracks being written on the tape, with read following write transducers. And it writes and reads the information on a strip of magnetic tape, which passes by the tape head as a piece of plastic with media on top of it. The actual recording technology used is probably about 10 or 15 years behind that being used in hard disk drives. So in a sense, you can say they've got a roadmap from the advances in the hard disk drive technology and where they can take this. Modern magnetic tape cartridges also include some flash memory for recording metadata about what is stored on the tape, which improves data access and tape longevity. An interesting aspect about this also is that people are actually using flash memory to feed magnetic tape in the drives. The reason why is because when you get a drive mounted, it's really fast. It can read and write data really fast. It's just that you have to, traditionally they're using libraries. They have to have a robot goes to a shelf, grabs the tape, sticks it in the drive, and that's what takes the time. But they actually read and write when they're in the drive very quickly. So let's see. So here's a roadmap for the tape. And this is the LTO roadmap, linear tape open, which is the dominant tape technology out there today. It's now available up to generation 10 with 30 terabyte native capacities. They projected it to have up to 36. It ended up being announced like a week ago with the 30 terabytes. And IBM also is selling their own version of a tape. They actually make all the drives, and they also it's basically the same media sources, but their tape storage capacity is up to 50 terabytes per cartridge. So based on this roadmap, did we run out of juice? Oh, we're out of juice. So based on this roadmap, likely by the end of the 2030s, the native LTO tape capacities could be close to 600 terabytes. So it's not out of question that you could have a 1 petabyte magnetic tape cartridge sometime next decade. So they're less expensive than hard disk drives on a dollar per terabyte basis, although the tape drives are much more expensive than a hard disk drive. They're like, say, $5,000 to $400, for the drive. Yeah.
Just momentary digression.
Yeah.
Since you're here and we're here, tell them where magnetic disk and tape technology came from originally.
Oh, yes. Well, the magnetic disk technology was invented on 99 Notre Dame Street in San Jose, California. And the building is still there, although you can't see the IEEE milestone plaque or the ASME milestone plaque there either. Tape, maybe that was in New York, because that was IBM also, but
Wasn't that the labs?
I don't think so. I think that's probably I don't believe that was done at the labs here. But the hard disk drives are basically developed in the Silicon Valley here. It wasn't Silicon Valley. They were kind of large. They were like, the discs were this big. No, I think they're about this big.
It's tall.
Yeah, it looked like a washing machine held by 3.7 megabytes of data, the first one. Now there are other ones.
In the museum.
Yes, yeah, in the Computer History Museum. Now there were people like Bryant, folks, they made some drives like that, for instance. So there are some big ones out there. So that's tape and hard disk drives. Now let's move on to solid state storage, flash memory and SSDs. So flash was originally an extension of the floating gate method of manufacturing non-volatile memory. The first sort of floating gate memory was the erasable, programmable, read-only memory. And I know some of you have worked with those. It was invented in the 1960s, but was not developed until the 1970s. In EEPROM, like in dynamic random access memory, DRAM, and read-only memory, ROM, each memory bit was represented by a transistor. Today, almost all NAND flash uses charged traps rather than floating gates, the original technology, to store the electrons, which enable this memory technology. Now, this was a planar process for many years. It just made one layer of NAND flash. However, as the lithographic features approached 15 nanometers, it became much harder to make useful planar flash memory cells. It couldn't do it. And that prompted the development of 3D NAND flash, where the flash memory cells are stacked on top of each other to create layers. Samsung announced the first 3D NAND in 2013, but it wasn't shipping in volume until 2016. By 2019, 3D NAND products are available from all vendors in 3D NAND production capacity planar NAND. In 2024, 2025, we're shipping products as over 300 layers, and maybe we'll hear more at the Flash Memory Summit. We'll find out. And with QLC SSDs capacities of 60 terabytes or higher. And in fact, I just came back from the Pure Accelerate conference. They announced a 300 terabyte direct flash module. Their last one was 150 terabyte. And there are some now, there's 60, 100, some out there. They're not cheap, right? It's like 6 times more expensive per bit. Okay. But if you want to have something in a lot of capacity in a small space, this would be one way of doing that. So now there's SSDs that are increasingly used for primary data and data centers. That is because they're fast. They'll spend the extra money on them because they need that to feed, for instance, AI, to feed the HBM memory in AI or regular processes. And hard disk drives that are being used as secondary storage. And the pure guys like to think they're even more secondary storage. Or people want to replace the hard disk drives. So the SSDs largely replace hard disk drives, as I said before, in personal computers and other client, consumer applications. Now, IEEE has a group within our Future Directions Committee that creates technology roadmaps, which includes semiconductor technology roadmaps. And the image on the right here is projections for NAND flash from that roadmap effort out to 2037. Projects at that point NAND flashes up to 24 terabits per die and over 1,000 layers. So if you buy those numbers, it's a big thing. Also an important element in is the development of interfaces that were built around these new faster storage devices that had different characteristics than electromechanical devices like hard disk drives. In particular, non-volatile memory express, or NVMe, was developed. It uses the PCIe channel in a computer, and it was built basically for fast devices. And it enables, you can also extend these performance advantages over a fabric. So now I can use this to make a network of these devices as well. And also I might say that even the hard disk drive guys have been demonstrating, like Seagate, demonstrating NVMe native interface hard disk drives, though they're not manufacturing them yet. So it's possible that the standard interface for computing somewhere down the road here could be based upon NVMe running on the PCIe bus. So let's look at optical storage. Mentioned before, there's a bunch of companies that are involved in this right now, which is really interesting. We'll talk about the approaches that were made with Blu-ray and the archive discs, which Panasonic and Sony were building on that as an archival storage media to competing against tape. There are also some newer than others, optical storage technologies contending also for these applications. They include pickle film, DOTS, I think it's DOTS 42, Project Silica from Microsoft, Folio Photonics, Cerabyte, Optera, and I forgot one, which is S Photonics. So optical discs have been used in archive systems for years. There's some people that like to use them rather than tape. There have been many approaches to optical storage, many using conventional looking optical discs and drives. The archive disk, Folio Photonics, Optera are examples of that. And some using tape-like system, pickle film and DOTS. And then there's volumetric recording projects, which Project Silica from Microsoft and S Photonics. They're both developed by a professor from the University of Southampton in the UK. And they use sheets of glass, of ceramic on glass in the case of Cerabyte, or they're actually writing within the depth of a quartz crystal in the case of Project Silica and S Photonics. So looking at some of these, here's this heroic project by Sony and Panasonic with extension basically Blu-ray technology, originally released in 2013. This roadmap was projected out to 1 terabyte disk capacities using layers of Blu-ray write-once optical media. To date, up to 500 gigabyte disks have been shown in industry events, and actually they're still shipping apparently in China, but you can't get them elsewhere. Yes?
What is the idle lifespan of this?
Oh, actually, it should be very long. It's probably limited by the life of the plastic substrate, if you treat it right.
50 years on?
Could be easily 50, maybe 100. And also the thing that if you have the inorganic optical discs, one of the big things that they've been advertising, they could store it in seawater and pull it out. You can read it, you know. So it's fairly durable. But you know, but even so, you've got a plastic substrate. So eventually, especially if you're not kind to it, good things won't happen to that. So that was that one. Here's this Folio Photonics things. So they want to create multiple layers for write-once recording where the layers are co-extruded and then placed on the plastic disc substrate. I've heard numbers up to 64 layers. The layers used are thin enough that several layers can be written on with a conventional laser, allowing higher recording densities than those projected for that Panasonic and Sony archival disc. They said that they should be able to make optical discs with 7 to 10 terabyte capacities by the 2030s. So that's another one of the contenders. Here's this interesting company out of Australia. It's called Optera. They use conventional looking optical discs, that's the plastic substrates, but the method of writing and reading data is different. Optera uses a special nanocrystal media with samarium in those nanocrystals, which have close but not quite the same optical absorption frequencies. So writing is done using what's called spectral hole burning, where the write laser frequency is adjusted to write on the particular nanocrystals in the laser beam, generating holes at particular absorption frequencies. So it's basically it absorbs or emits light differently where the nanoparticles that the laser of a given frequency acts upon. So data is written on both in the frequency of these holes in those individual nanocrystals as well as the depth of the holes. So you kind of see that in these pictures that are showing what that might look like. So reading requires a light source which has multiple frequencies to access all of the spectral holes with sensitivity and signal processing that can determine the hole depth. They say they can use this method to achieve a 10 terabyte disk for about $1 in this decade and possibly even lower costs using a multi-layer disk or maybe smaller nanoparticles. Anyway, so here's the Project Silica and the S Photonics here. So working with the University of Southampton in England, a professor there, Microsoft is working on their own archival media, storing data in the volume of a rectangular quartz crystal. The professor from the university started his own archival storage company recently, which is S Photonics for volumetric recording. There's a company called Cerabyte also out there, which is using a ceramic coating on a rectangular glass substrate, not the quartz, that is written using high-powered lasers, recording data patterns using MEMS devices like those in a digital light processor for digital projection systems, but actually recording what looks like QR codes progressively on the surface of this thing. That's how they encode the data. So there's a bunch of that out there. It's really interesting that Archive has gotten all this attention, especially with the optical stuff. But there is one more interesting technology out there, and someone brought that up earlier, which is storing data on synthetic DNA. So there's a few companies out there that are working on this. One was the Iridia I mentioned before. Twist Bioscience up in San Francisco was doing that. A few months ago they spun out their group that had been working on that with a few million. No, it's over $100 million of funding apparently. That's apparently still pursuing that. So this is something that's also being done. The Storage Networking Industry Association, which I've had some interaction with, I've been a member of that as well for many years. They did a road mapping initiative and are working on a DNA storage roadmap. So there are established companies working on this. It was a $155 million investment for the Twist spinout. That's what it was. And encoding is done with bases in a synthetic DNA strand. The two most common approaches to write, which basically you're adding molecules onto each other to make the data, to record the data. The two most common approaches to this recording are sequencing by synthesis and nanopore sequencing. Synthesis can make millions of copies at once. So if you want an awful lot of copies of a data, this can give it to you all at once, or all at the same time anyway. There's several companies exploring DNA storage, including Atlas Data Storage, spun out from Twist Bioscience. That's the name of that new company. Iridia Biomemory and Catalog Technologies. So that SNIA DNA group has envisioned a DNA storage channel that mimics that of a communications channel. So you can see the model here. The DNA channel has somewhat different layers than the conventional OSI communications model, though, of course, because they're recording data. So that's some of these storage devices that are out there. I'm going to get into one other class of devices too, the non-volatile memories that may eventually replace some of these volatile memories later. But first, let's talk about some of the changes in architecture and computing. Traditional basic von Neumann computers consisted of a control unit that controls the operation of microprocessors, a central processing unit, CPU, that contains the arithmetic logic unit that does mathematical operations, as well as registers for data being processed and stored. A computer can also have cache memory for temporary storage of data, as well as random access memory, DRAM, for example, that serves as the main memory used by the computer. There's usually also a mass storage device like a hard disk drive or an SSD that stores the rest of the computer's data that you don't need right away. But there's movements away from that traditional von Neumann architecture, which uses a lot of energy to move data around between all those different places. And a lot of time is wasted too, if you had a more efficient structure. So those energy and time issues can be addressed by moving from that kind of architecture to, as illustrated on the left, to a more memory-centric approach, as illustrated on the right. And this led to protocols like CXL. CXL supports memory disaggregation by removing some memory from behind the processor. You still need some memory close to the processor to support it, but it's moving data. It allows you to augment that data with CXL. Memory pooling is another possibility. So I move some of the memory away from the processor. I can actually store it as a pool, and I can share it between processors. And that allows you to more efficiently use that memory and be able to address new problem classes, and also heterogeneous computing, which allows data to be processed by a variety of types of accelerators, which, for instance, in CXL could be part of that CXL storage network or memory network. Note that memory-centric system includes a low latency DRAM connected directly to the CPU, but then you have this far memory with a little bit of latency on it, maybe a nanosecond or so. That would be in the CXL pool. So CXL has a lot of interesting possibilities. By using that and it's running on PCIe, removes processors DDR limitations and how much memory you can get on the channel, and also the types of DDR interface. You could use DDR4, DDR5, but you can't use both. CXL allows the memory to use any interface and any type of memory. because it hides the differences between them. It supports memory disaggregation. That means, for instance, if you have traditional servers, you've got memory of the servers. That memory is kind of stranded, even if it's not all being used. But if you share it, then you can more effectively use it if in the right way. So memory pools can be dynamically allocated between the who's using it. And various types of memory can be used as memory pools. So I can hide the differences between those memory. So data sets also can be moved from processor to processor. It runs on the PCIe bus, and it also paves the way for an interface that's being used. One of the proposals, an open interface for chiplets, which also is compatible with the PCIe bus called UCIe. So this PCIe bus is a big deal, right? And there's the NVMe as well as CXL and this UCIe. They essentially are run on the PCIe bus, and it's being used to provide a mass market high performance protocol that basically doubles its performance with each generation. And that enables faster data movement for common storage and memory tasks over time. And in fact, I think recently they started, there was some announcements on the PCIe version 7. Right now, people are shipping with version 5, version 4 with shipping now with version 5, but they're actually looking on future generations like PCIe 7 with very high performance, which would then support all these other functions. So CXL, the 3.0 version, originally was proposed by Intel as a way of enabling their Optane non-volatile memory to be shared in a memory pool with DRAM and various types of domain-specific processors. So Intel was a big driver for developing this CXL. CXL enables memory expansion that's not limited to capacitive loading and pin count, as the direct attached memory is. Some additional interfacing with the switch is required to do this, so memory in the memory pool has some higher data latency than direct attached memory. So you probably need some direct attached memory, but also then augment that with this shared memory. So NVMe, as I mentioned before, there's been some drives that have been at least demonstrated with NVMe interfaces. And even magnetic tape drives might eventually be using this as well as SSDs. So it could become PCIe and NVMe over PCIe could become the common transport or the common interface for storage devices in the future. It can be a transport over common fabrics like Ethernet to enable storage pools, similar to the way that CXL over fabric can be used to make memory pools. So this gets into this general idea of breaking up traditional computing into pools of the various elements of computing. That could be the storage pool, memory pool, compute pool, possibly even a networking pool, where you have some local support, but then you have some resources that are pooled and then used by software to allocate them to different means. So that's a composable infrastructure is what they call that, where you can essentially build up virtual infrastructure with software from these pools. So let's get on to chiplets, but these aren't the kind you eat. So why do we need chiplets? So lithographic scaling, what was seen as traditionally driving what's called Moore's law, is getting harder and more expensive. There's still people looking at even sub nanometer, and people working on bringing some nanometer devices, but the machines used to make these, like the ASML lithographic devices, are several $100 million to buy. So it's pretty expensive to buy the equipment to make these. So not every device needs the small lithography. Not every function needs small lithography. So the idea about chiplets is, what are the things where I could use this real small lithography, like logic, right? I want to be able to do a lot of dense logic. That's fine, but then I could, like memory, networking, other things. I could work with bigger lithographies, less expensive processes. I can make individual little dilates that's the chiplets, that then I can combine with a high performance interface in a package that basically would be like an ASIC deconstructed, okay, or deconstruct traditional processing and build into these pieces. This is becoming a big deal. I was just at an IEEE conference on packaging a couple weeks ago. A lot of stuff talking about these chiplets, and this reduces the overall cost of the electronics. And if the chiplet interconnect standard is open, allows competing chiplet manufacturers and chiplet foundries where these can combine in order to make a total functioning device. I can actually create an infrastructure and a market for these chiplet devices for various functions. Now we've got a whole new type of potential industry and ways in which I use semiconductors. It goes beyond that, but we're using this today. If you look at that GPU I showed you that Jensen Huang was showing, which had a lot of HBM memory on it, by the way. HBM memory with GPUs. HBM by itself is an example of chiplets. There are a whole bunch of DRAM wafer die stacked on top of each other, now up to, I think, 16 high, and they're talking about going to 24. That's an example of chiplets, but that also connected with the GPU is an example of that kind of packaging. It's having a standardized chip architecture will enable us to become even more widespread with multiple vendors, chiplets, components to be used, and the creation of foundries where you put these together to make functional devices. So UCI is an example of a standard. It also runs that PCIe or compatible with the PCIe bus. It can be used for connecting 2D, which is planar die, and 2.5D, where I have some stacks and also the planar die, to connect those high performance, connect those into essentially what's a deconstructed system on chip package. Uses range from handheld devices to high-end users, servers, and things of that sort. The standard permits mixing and matching dies from multiple sources. It's an open standard. And it combined with CXL through a UCIe retimer allows extending off package to connect with other media, for instance, optics, electrical, or microwave even, to access memory storage and processing pools. So there's even more interesting things you could do with these things. But this is not the end of this. The next step is heterogeneous integration, where we're actually stacking die of all different types on top of each other and creating interfaces between them. It could be optical, it could be through silica holes, it could be microwave connections of various types, where interacting chips of various types include processing, memory, communications, networking, various other things. However, these non-volatile memories use a lot of power because you have to refresh them all the time. So going to these 2D, especially to this 3D heterogeneous structure, I think opens up new possibilities for memory technologies that do not consume the heat, that do not create the kind of heat that you'd have to dissipate in these heterogeneous structures. So just a little bit more on this. I can use different types of memory with chiplets. That's another thing about that, including volatile memory, like DRAM with non-volatile memories like magnetic random access memory, resistive random access memory, ferroelectric memory, and also phase change memory. And by the way, phase change may come back. I heard that SanDisk may be working on it. The component chiplets can be made into a standard like UCIe, enables multiple vendors to supply these components for a resulting chiplet module. So this could be an interesting expansion. Now, an example of the chiplet memory. First of all, some of the traditional memories, embedded NOR can't shrink below 28 nanometers. So that's a limit. If you want to make a smaller memory device for like code storage, that's what NOR is commonly used for. You can't make something smaller than 28 nanometers. Embedded SRAM eases off its scaling at about the same process. It doesn't reach a hard stop. It simply doesn't scale with the process anymore. These emerging memories, though, that I'm going to talk about shortly, have a lot of room to scale, and some even improving performance the smaller they shrink. So let's look at embedded SRAM as a technology that could easily yield to an embedded emerging memory, even today. So the chip at the right is an Intel microprocessor. You will note that slightly more than half of its area consists of SRAM, static random access memory. Part of the reason that this SRAM cache is on the chip is because it's so fast compared to DRAM. But an emerging memory is also faster than DRAM. And even though it may not be quite as fast as an on-chip SRAM cache, it can be significantly smaller than the SRAM at an equivalent cost. SRAM is like 6 transistors per cell, right? And these emerging memories are going to talk about are single transistor. So at equivalent cost, and the cache designs involve trading off size against speed. Since a processor chip is made on a high-performance CMOS logic process, its cost will be pretty high. If you try to build a memory on that too, that's also high. So in each bit, as I said before, each bit in a SRAM uses 6 transistors. And it's easy to see that the separate chiplet approach could save you, could cost far less than this SRAM that's built into the device. So again, seeing some of the reasons why we're probably going to be going to these kind of structures, and also leading us to consider new memory options of what we can do. So let's talk about those non-volatile memories. So they're basically emerging memories are going to replace some of the current memories we use every day. Leading edge processes can't use NOR. SRAM is getting on less attractive. It's not shrinking the way the logic does. There's already some use of this in the enterprise. I'll show some examples here. There's also growing adoption of some of these memories in embedded devices, especially in consumer and industrial applications. Increasing consumption, as we do more of these things, it will lower the cost. The big thing that killed Optane, for instance, was that it could never get up to the high enough volume that their costs of manufacturing below what they had to sell them to compete against, to be an adjunct to DRAM, for example. But if you get the volume up high enough, then it can do that. Especially that's an issue for standalone memory versus embedded memory. So plus they offer technical benefits. They're fast, they're low power, and they're less messy than flash. They have more flash memory has a longer write than a read process, and so they're more equivalent on writing and reading, for example. So various types of emerging non-volatile memories are available for chiplet or other applications. These are magnetic random access memory, or MRAM, resistive random access memories, or ReRAM, phase change memory, or PCM, and ferroelectric random access memories, or FRAM. So these are all single element cell devices. They support small and inexpensive die and 3D stacking. They promise to scale past DRAM and NAND flash. They allow write in place. There's no block erase like you have with flash. And they're more symmetrical read and write speeds. They're also non-volatile and persistent. That means you don't need to refresh them. You don't need to chew up energy, making sure the data stays in the device. So these are some of the advantages here. And here's the timeline that my colleague Jim Haney and I put together on how these memories may replace some traditional memories. You see at the top there, embedded memory, NOR and SRAM are the big candidates there. NOR, again, is used for code storage. SRAM is used for cache. For instance, it can be used in an inference device to store weighting functions from an AI training. And there's actually products out there today which are include some SRAM and a lot of MRAM in them that are being used in some consumer applications like Fitbit, watches, things like that. But we think that by the getting into the next decade, that there's going to be a lot of replacement with NOR and SRAM in these devices. With discrete memory, I think there's again a little bit further out, but still happening. We believe, and then the chiplets, high bandwidth memories, and other devices that these technologies are going to have a place. But again, a little bit pushed out in these things. So with that, if you're interested in these technologies, my colleague and I have a report, have a flyer here. If you like one, you're welcome to have one. And also I want to invite you, I'm the general chair of the FMS 2025, the Future Memory and Storage, where you can find out some of the latest developments in digital memory and storage technology, August 4th through 5th at the Santa Clara Convention Center. I also have a flyer on that if you're interested. So in summary, the data demand's exploding on Earth and beyond, and architectures are developing in ways that human cleverness can get beyond physical limitations that we've run into. That's developing all aspects of this storage and memory hierarchy and the ways in which we connect them and use them. Hard disk drives, magnetic tape, use magnetic recording. Hard disk drives are available up to 36 terabytes today. More in the future. Hard disk drives as high as, magnetic tapes as high as 50 terabytes. Solid state drives use NAND flash memory. NVMe interface. NVMe is the interface now dominating that. They're available up to 300 terabyte devices right now, though not cheap. But the hard disk drives, magnetic tape, are used for colder data. Because of the speed and the performance characteristics, NAND flash and SSDs are being used for primary data in data centers nowadays. And there's new developments in optical and synthetic DNA technology, which may have a role in the digital preservation and archiving. And embedded application driving growth of these emerging non-volatile memories, which we believe that eventually will become much more widespread and be part of this whole storage and memory zoo. So with that, I want to thank you for the opportunity to talk to you tonight. I guess I'm open for questions if you have any. Yes, sir.
When you're talking about the tape drives,
Yes.
is that per single cartridge with the storage amount? Or
Yes. It's per cartridge, the half-inch cartridge.
so typically, how many cartridges in a single library unit?
It all depends. But there are some humongous library units. I saw like could be many petabytes or actually, I think it's actually exabyte libraries out there. I saw one at CERN that was at least as long as this room, the library system, for example. So that's a big one.
Tom,
Yes.
could you please repeat the questions?
Oh, I'm sorry. They're asking how big a library system there can be. And I was saying, I think there's tape library systems. And I think there's tape library systems that are approaching like an exabyte of storage capacity. Yes.
So probably I see back related to a more complex chemical stew of making all of these parts.
Are you talking about particularly bringing in these new memories into place?
Does normally bring anything magnetic into the stew, it's bad, right?
Well, it all depends. But right now, the MRAM is the magnetic one, and that's done as a back end of line process. In other words, I basically have done all of the logic, and now I've got an interconnect layer, and then I build the MRAM as a back end process on top of that. So it's not being,
Don't forget to repeat the question.
oh, sorry. Thank you. The question was bringing new materials into semiconductor processing technology. Semiconductor processing. The example might be with magnetic materials for magnetic memory that was part of a electronic device, part of a semiconductor chip. And the answer is it's generally done today as a back end of line process. After all of the logic process has been done, then they build this on top of it.
So we're sailing ahead. Everybody has a roadmap for a particular project.
Everybody has, and they're all going to compete. We'll see who wins.
Okay.
Yes.
Question from remote.
Okay.
What's the exponential breakthrough needed for this technology to begin adoption? He didn't specify what technology, but
The question was, what is the
what's the exponential breakthrough
needed
for this technology? They didn't name the technology.
for some technology to be adopted?
To begin adoption.
Okay, it depends
So
on
maybe that was for a technology that wasn't yet adopted, maybe the DNA, I don't know.
could be DNA, it could be optical. The big issue with DNA is the read and write speed.
So again, repeat the question.
Yeah. Oh, I think I did, didn't I?
Oh, okay.
Yeah. So the big issue with DNA is read and write speed. So right now it's pretty slow. And it's also a chemical process, right? So it's not going to be, nanoseconds probably goes in the chemical process speeds. But the argument is that since we have DNA and DNA is being used for medical purposes, that people will find faster ways of be able to read and write DNA. Writing maybe for trying to fix genetic problems, for example, and reading in order to be able to find out people's, medical genetic information. And so we'll get faster at doing this stuff because of that. So that is a possibility. And DNA is interesting in that it can, in the right circumstances, especially if it's dry and kept away from air, can last a long time. So it might be a good, and people have extracted DNA from, dinosaurs and mastodons and all kinds of stuff that isn't around anymore. So the argument is that the stuff could last. And since you can make so many copies at once, you can have enormous redundancy, with DNA. So for and archival media, it has some interesting characteristics because of that. On the optical side, there's a lot of things that there's some of these are using new types of technologies. Being able to write and read again is some of the big issues. So how can I make cost-effective, practical read and write devices for, say, the Optera approach or the S-Photonics, Project Silica, or a Cerabyte? Can I reduce that to practice and make it something manufacturable? And will it be reliable? Those are all the things that have to be figured out.
So the remote question person, Brian, added some details. Are there differences in DNA from human/lab/others?
So this is the DNA that we're talking about here is synthetic DNA. It doesn't work in an animal, or so in fact that's probably although it is interesting to think about if you can store your family history on your DNA, for example, but what they're talking about for these applications is it's just something that is it's synthetic. It doesn't relate to life forms per se. It's just using the same mechanism that builds animal DNA into a data storage technology. Oh, I think he had a question there.
I guess, how do you see like compute in memory interacting with some of these technologies? So I think it was like SK Hynix was the demo of like putting like an adder right next to your memory cell in DRAM.
Yeah, I think those are other technologies that could be very useful. And again, it reduces that. If you can process data closer to where it lives, it's faster and it uses less energy. When you move data around, it chews up energy and takes time. So those are other useful approaches. Now, there's even things beyond the traditional approach. For instance, most of these devices are using currents. They're using electron charges to work. Now, MRAM uses spin, another property of electrons. There's people that are talking about spintronic devices that could be logic devices built using spin rather than charge. If so, maybe you could build devices that don't have resistive heating and therefore would generate less heat energy, less wasted energy overall, and more energy in the processing if such devices could be practical. Now, those are quantum mechanical devices, so but it's a possibility.
Just to finish the earlier question, Greg, didn't you have a program about 10, 12 years ago, a Silicon Valley company would let you order DNA over the web, and they would just manufacture it for you to your specifications and send you files of that DNA.
Well, that's cool.
Do you recall that?
That could be, I don't remember that.
Wow, look it up.
There's still companies that do that.
Yeah, so this I just wanted to bring up that this technology of creating a DNA custom has been around for more than a decade.
Oh yeah,
About.
and there's been lots of demonstrations, as you say, you can do it. It's just doing it cheaply and fast. That's the trick. Oh, you haven't had one yet. Now I'll get you. Go ahead.
How do you see memory evolving to support chip-to-chip interconnects? We're seeing more adoption of like coherent caches being shared between processors. Yeah, so what do you see in terms of the roadmap for that?
So the question was a roadmap for the
Memory that supports chip-to-chip interconnects.
that supports chip-chip interconnects. So that would be like a UCIe or something like that, right? So you're talking like for chiplets?
More like GPUs and CPUs sharing L1 cache, L2 cache. And they all have a coherent address space, which makes it easy for like a CPU and GPU to access the same data without
Sure. I mean, things like that make some sense too. Is that just using the PCIe bus, or is it
it's over PCIe, but I think it's I don't know what the memory technology is, but
yeah,
I'm seeing more of these sort of applications being used. So.
Some of these might be that CXL I was talking about, because that's meant to be a memory, essentially a memory fabric, and sharing resources between and those devices, those systems based on those devices should be coming out. So that might be what it is. Thanks. Yes.
So can you talk some about latency? We talk about the CXL. It's nice to have a big memory pool, but money can buy bandwidth, but latency is forever, is the old stuff. What kind of latencies are they talking about?
I think it added like a nanosecond or so. Oh, the question was on latencies, especially with the CXL. So it's a switch network, but I think they've got the latencies at something like a nanosecond, something like that. So it's not, it's some, but it's not a huge amount. Still keeps you, below the, below level. A lot of things would work with, maybe not everything, but a lot of things could deal with that. And you still keep some memory close to the device because you still need that, the lowest latency you can get for most things. But then you feed it from this other memory, for example, where that's appropriate. In the back, we got two of them.
Does that support write the storage dynamically or just read only?
So the question was in the optical storage, does it support writing dynamically or read only? And I think what you're asking is it a worm device? Write once, read many times. Is that right? These mostly are worm devices.
Okay, so
Yeah.
the optical storage just mentioned, does it like can write as well or just?
Yeah, they write information, but you cannot overwrite it in most of these devices. So it's basically an archival worm storage. That's the write once, read many times. That's how it's a worm. Yeah.
Wondering if, given trends in transfer, people are going towards more quantization and like lower bit representations. Are there any ways that like memory can take advantage of that or lower the requirements?
Probably are. I mean, there's especially like you think like AI and stuff like that. Yeah.
Good question.
Oh, say it one more time so I can try to represent it right.
Impression.
With
Oh, is it compression you're talking about? No.
Yep.
No, go ahead. Go.
you're saying repeat the question.
Yeah, repeat the question.
With AI inference moving towards lower bit representations.
Lower bit representation, less accuracy, essentially.
Less
Yeah, yeah.
Are there similar physical instantiations of that type of memory to take advantage?
There probably are. You know, I mean, if you're relaxing on the computing, you know, I mean, you have to be careful. You still want to be accurate enough, but I think the thing is, for some things, it don't need to be so accurate. It doesn't need to be the absolute best, right? And so, yeah, there's going to be, you know, that's going to change some requirements for memory and storage to support that. But you're still probably going to have a lot of data you're working with, so you're going to need both. Yeah.
So I'll follow up on
Yeah.
that. I think the right one to read many times. And it will be perfect for a lot of use cases. For example, large language model, right? So model train is fixed or blockchain. Build a block and then save out there, don't need to change. So I just wonder, enough for adoption, economically, is it cheaper than other alternatives or what the advantage of using that?
So there are two things he was saying. One of which is an observation that the optical well, I think the big question was, is it cheaper? It can be, right? So yes, that's the whole idea behind it. And that's why there's all these startups. And they also sense that this latest generation of LTO tape, which is the most common tape used for archiving, is not backward compatible even in the past generation. They changed the formulation. Apparently that made it incompatible. Plus, it's not the capacity that they were advertising originally. So I think that plus the fact that people are saying, AI is going to use all this data. We're going to save everything. We don't want to save it on anything expensive. You know, tape may not be as extendable as it was. So are there alternatives? Gosh, maybe optical would be that, or DNA, you know, and so, but I think the optical, that's a lot of the arguments being made. We're going to store so much information. We need cheap media to store it on. I have the optical storage technology that can be made cheap. That's that. I think that's the argument, you know, that they're using. Yeah.
Two questions.
Yes.
One for me and another from Brian Remote. So first for me, on the DNA, it seems like it would be a sequential read. Like
Yes.
tape.
It is like tape in
There
that
are
sense.
things you could do the way there's, 23 chromosomes, you have like one strand per person's data. But then you have to be able to access every person. You have to have some index to start the read of the sequence. Is there some way of doing that with the DNA?
I think there's ways to create some kind of call it metadata or, sectors, DNA sector information, things of that sort. So I think some of the things we've used for other technology can be applied to DNA as well.
Okay.
But also you might even consider I could do multiple strands at once with different readers or something, so I can get faster performance.
Like reading multiple platters on the disk drive.
Yeah. Yeah, and I can make 1 million copies of a DNA at once, with the synthesis method. So I have a lot of things I could try to read simultaneously if that worked and it was cost effective enough.
The question from Brian is, were there lessons learned from 23andMe? So that website that would analyze human DNA.
Yes, 23andMe was, so the question was, there were lessons learned from 23andMe. So 23andMe was a company that offered to give you your DNA, they'd give you maybe some ancestry information based on that. But their big thing was that they're going to use it for getting medical information from the people that use the service, and then using that to help other companies to develop new medical services, treatments, methods for scanning for vulnerabilities to different diseases, things of that sort. I think there certainly are lessons, but probably not for DNA storage. We exhausted? Ah, one more. Okay.
I can go. Are you know what people are doing in terms of like the physical interconnect to memory? So you talked a little bit about UCIe, which is this protocol, but there's things like I think some of the newer memory standards use like PAM4 encoding actually over the wire. So are people pushing further in that direction of like trying to get more data on the wire on the interface, or with like the integration, you can just go back to good old NRZ and like not have to worry about it?
So I think so this is like the encoding method, kind of what you're talking about. The question,
the actual like interconnect between your compute element and the memory.
so the question is regarding the interconnect between the compute element and the memory. Okay, so what they've used for a long time, a lot of memory, is the DDR, right? And that has limitations on what you can do with that. So the idea of getting an interface that runs on PCIe, like CXL, is an attempt to do that. But are you talking about within the chip itself, or are you talking about between chips, for example? Or
Either.
Yeah.
Because I know a lot of the costs in terms of like accessing memory is the energy you have to spend to actually like wiggle your pins
to move it
to the to the DRAM.
Yeah.
So like, what are people doing to try to reduce that expense, I guess?
Well, a lot of it's having to re-energize it all the time because the memory decays in a DRAM, right? So they have to refresh the data in it, and that's where a lot of the energy gets consumed in it. There's also energy consumed in moving data around, and maybe is that kind of what you're thinking about?
Yeah.
Yeah. The interface, and its efficiency and capability to have things to do with that. But I guess I don't have a direct answer to your question on that. I can tell you some of the stuff people are doing, but thanks. Yeah.
We might want to save some time. I think the person from IEEE wanted to
Oh, yes.
have some things. So we could have the IEEE gentleman have some presentation, for a slide, and then our speaker now, and our speaker can answer other questions.
Thank you.